Assalamu alaikum. How are you?
Assalamu alaikum, sir.
Assalam, sir.
Walaikum assalam. Okay, so we have our first class after the midterm. In the previous class, we have covered chapter 3, 3.5. We have started 3.5. We have covered the basic concepts of TCP, TCP header format. Then we have also covered some of the interesting scenarios in TCP. And as we have mentioned that in the final syllabus, we have 3.5 and 3.7 of our chapter 3, and then chapter 4, 5, and 6. So any question, anybody on the previous class? You have to understand those interesting scenarios
Sir,
to understand
আমার
how TCP.
স্যার একটা কথা ছিল
Yes, Sadikun.
স্যার স্যার আজকে তো স্যার ওই ভ্যাকসিনের ডেট স্যার তো ভ্যাকসিন
Yes.
দিতে যাইতে হবে
Okay, no problem. You can leave, no problem. Just
আইডিটা লিখে দিব
yes. Give your ID in the message box, and then you can leave. Okay.
থ্যাংক ইউ স্যার
Okay, thank you. So,
স্যার হ্যালো
yes, Mahir.
স্যার আমার 3 নাম্বার এক্সারসাইজে একটা প্রবলেম আছে।
Okay. Exercise or okay, exercise 3, right?
যেটা স্যার মানে করতে বলেছিলেন
Okay.
লাস্ট ক্লাসে।
Let us show the exercise 3. That's good. So this one, right?
জি স্যার, এখানে
Okay.
সি নাম্বারটাতে যখন আমার এটা আমার মিসিং হচ্ছে, পরবর্তীতে টাইম আউট হওয়ার পর যখন আমি আবার আমি ব্যাক নিচ্ছি, তখন আমার অ্যাকনলেজমেন্ট মানে বিটা সহ হবে না শুধু এর জন্য 450 হবে?
Okay, I got your question. So for this, okay, you have to do two things. Okay, first of all, both segment arrived at correctly at the receiver. Then the first segment is lost, right? First segment is
Yes,
lost. Sorry, first acknowledgement is lost, and there is a timeout. And the second acknowledgement arrives after the first timeout interval, right? So this is the scenario. Now, your question is, when we retransmit the first segment, definitely we'll retransmit the first one, right? So what was the sequence number? 300. That is sequence number 300.
এটা সেগমেন্টে প্রথমেই লস্ট হয়ে যাবে না?
No, this is question C, right?
Yes, sir.
Question C says, suppose the two segments sent by A arrive in order at B. So B actually received both. The problem is the first acknowledgement is lost. See, the first acknowledgement is lost. So data is not lost. Data is lost in question number B. Question number C is a separate question. You got my point?
Yes, sir.
It's a separate question. So in this case, the first acknowledgement is lost and the second one arrived after the timeout. So definitely after timeout, the first sequence will be retransmitted. So 300, 150 byte retransmitted. Now your question is, what should be the acknowledgement number, right?
Yes, sir.
Okay. For this, if you have any confusion, just write down the buffer of the receiver. So definitely receiver has received both. That means from 300 to 450, and then from 450 to 550, right? Remember, I have corrected this as 450.
Yes.
So both is received by the receiver, but unfortunately, sender, before the timeout, sender has no way to decide whether receiver has received both. Sender thinks that receiver did not receive the first segment, so it will retransmit the first segment. But when you consider the acknowledgement, that is sent by whom? Receiver or sender? Acknowledgement is sent by the receiver or the sender?
Sender.
Acknowledgement. See, think, acknowledgement is sent by B or A. Who will send the acknowledgement?
B.
So B is the receiver in this case, right? Always acknowledgement is sent by the receiver. So now see, from the receiver's point of view, receiver has received both, right?
Yes, sir.
So what will be the acknowledgement? Updated one?
550.
550. So no, not 450. It will be 550 because acknowledgement is sent by the receiver, not by the sender. So although sender retransmitted 300 for 150 byte, that means it seems it can be 450. But if you think about the receiver received both, and will receiver will be sure that this is a redundant segment. It was not necessary for the receiver, but receiver would understand sender has retransmitted this because sender did not receive any acknowledgement, so I have to send a updated acknowledgement. So what is the updated acknowledgement? That is 550. Clear? So logic,
Okay,
you
sir.
have to understand the logic here. Don't just understand the solution only. In the solution it is like that. No, you have to understand the logic. Okay, so that is any other question from the previous class? So what we'll do, if you have no more question, if you have question, more than welcome. And during the class we will do some hands-on examples. So again I will request everybody to participate. If you participate, your problem will be clear. If you don't participate, I think this will be complex to you. Okay, so first we'll do some hands-on examples. Then today we will cover the rest of chapter 3, and we will start chapter 4 in the next class. And probably our class test 4, right? Class test 4 will be held on 11 September. That is in your course outline. So if you can check, this is on 11 September. So we have one more class before that. So the syllabus will be 3.5 and 3.7, rest of chapter 3. And we will start chapter 4, but that will not be included in class test 4. Okay, and it might be online or it might be offline. I will confirm you in the next class. Okay, so now let us go back to some hands-on examples. Okay, let me come here. Okay, so let me give you an exercise on TCP. Okay, exercise on TCP. Suppose this is host A, this is host B, and there are 3 segments sent by A to B. The first segment contains sequence number, for example, 400, and there is X byte of data, and the next segment has sequence number 550 with Y byte of data. Okay, let us assume this one as 100 byte of data. Okay, 100 byte of data, and the third sequence number is Y with 150 byte of data. Now acknowledgement, okay, there is a timeout. Definitely there is a timeout for the, TCP uses one single timeout, right? So if one timeout expires, it will transmit the oldest unacknowledged segment. At a time, TCP will maintain only one single timeout. So suppose acknowledgement come anywhere, before timeout, after timeout, but in this case I have shown you before timeout, no problem. So in this case The first acknowledgement will be, for example, Z, and then acknowledgement will be P, and after the timeout, sender will retransmit the oldest unacknowledged segment, that is definitely sequence number what, that which one is lost, right? So 550 100 byte of data. And now what will be the acknowledgement number? Suppose this is Q. Now what you have to do, you have to find X, Y, Z, P and Q. So do it. Find your open your workbook, find your paper and pencil, do it right now, and send me the answers, just 5 values in the message box. Everyone, please take your paper and pencil. If you have any confusion in the basic, please ask me question, no problem. Your answer can be wrong, but if you participate, you will understand what actually you did wrong in the question. I will give you 3 minutes to complete that. Just assume every sender will always send back-to-back segments. It will send sequentially. So sender will not send out of sequence. So if you know it is sequential, you can calculate segment 1, segment 2, segment 3. And if a segment is lost, then always cumulative acknowledgement will be used. That is, it will receiver will send only the previous in order acknowledgement. Okay, try to solve this. 3 minutes. And in the meantime, let me take the attendance. So please respond and do the calculation in your paper pencil. Okay. Tanjina Hassan, please respond. Tanjin, are you there? Azharul Haq, Mushfiqus Salihin, Mushfiq, Abu Ammar,
Present, sir.
Azizul Hakim. Aziz, are you there? Azizul Hakim. Okay, Mahish Shahriyar present. Kamrul Hassan, Tanvir Rahman, Ishrat Jahan.
Present, sir.
Okay, Anika Tahsin, Shoumik Shirshaw.
Yes, sir.
Okay, Nuzhat Jahan, Farhanaj, Jahara Islam.
Yes, sir.
Farha, are you there? Farhanaj? No. Okay, Kausar Ahmed, Munjurul Asad. Kausar present? Kausar present? Okay,
Yes,
Munjur present. Okay, Enamul Bari,
Present, sir.
Mohammad Sabbir, Saima Khanum.
Present, sir.
Okay, Tawfiq Hasnain,
Present, sir.
Shihabuddin,
Present, sir.
Jannat Ara, Jannat Ara, Partho Protim.
স্যার ওর নেট সমস্যা স্যার।
Jannat present?
স্যার পার্থপ্রতিম।
Okay, Partho present. Okay. Ifat Ahmed,
প্রেজেন্ট স্যার।
Mahmud Hassan,
Present, sir.
Hasin Shahabuddin.
Present, sir.
Okay. Tanjina Hassan, Hasin Shahabuddin present. Okay, Shafiqul Islam. Shafiq. Okay, Ihsanul Karim.
Yes, sir.
Shariful Islam.
Present, sir.
Okay, Saudia Haq,
Yes, sir.
Noor E Nawaz,
Present, sir.
Shoaib Ahmed, Mehdi Hassan,
ইয়েস স্যার।
Wasiul Haq,
Present, sir.
Samiud Jaman,
Present, sir.
Adrita Mustafa. Mustafa, are you there? Ashikur Rahman. Sultan Mahmud. Sumaya Akhtar. Rahul Mullik.
Present, sir.
Sumaya, okay. Rahul Mullik.
Yes, sir.
Okay. Noyan Kanti.
Yes, sir.
Kazi Nafis.
Present, sir.
Mohammad Masnad Hussain.
Present, sir.
Mia Muhammad Azizur Rahman.
Present, sir.
Faisaluddin. Faisaluddin. Nazmus Sakib. Fahim Ahsan.
Yes, sir.
Moshiur Rahman.
Present, sir.
Kazi Maisun.
Yes, sir.
Okay. Anyone else?
Sir, Kamrul Hassan.
Okay. Tell me your ID.
0 triple
Okay. Last 6 digits.
087. Kamrul Hassan.
Kamrul Hassan 087. What is the previous three?
011 163
Okay, 163 087. Kamrul Hassan present. Next,
16 20
Sir,
15.
Jannatara 172155.
172. Just one by one. 172 155. Okay, Jannatara present. Next,
162015.
162015. Tanjina present. Okay, next, 171 234. 171. Farhanaj present. Okay, next,
Sir, 171107.
171107. Anika Rasin. Okay, next. Anyone else?
Sir, 161
162 162 then
077.
okay, Azharul Haq. Okay, present. Next. Anyone else? Okay, thank you. Okay, I did not see any answer already posted. Do you need more time or you cannot start? Anybody has solution? Mahir, okay, x equals to 150, correct. Put all at a time. Okay, y equals to 650. Okay, then z, p and q. Others, please participate. Any other answer, anybody? Z equals to 550, then P equals to 800, and then Q. Why Q 150? You should not be 150. But thank you, Mahir. I think you have the concept. So almost close to the correct answer. Some problems. Any other answer from anybody? Please post the answers in message box. Only one answer I got. Why? Okay, one more minute. Any other answer? Nafis. Are you there, Nafis?
Yes, sir.
What is the answer? Did you try?
Sir, I didn't attend past couple of classes, so.
Oh, okay. Why? Masnad, you had the answer?
Sir.
Anika Tasin, yes. I actually expected many answers from many of you. Only Mahir answered. No one else. Sumaya, Tanzina. Are you trying? See, I expect Okay. Okay. Let me give the answer. But if you don't try, it will be not easy to understand the things. That is where networking becomes tough. If you don't participate in the class, it will not be easy to understand the concepts. Okay, Sumaya, very good. X 150, Y 650, Z 550, P. Okay, again close, but just a little bit of concept. But at least you have the concept. Very good. Any other answer? Anybody? I always ask you to participate in the class, even if your answer is wrong. No problem. You will not be hurt. Doing wrong in the class activity is much better than doing in the final exam, right? So if you don't participate, it will be tough to accommodate the things. Anyway, let me give the answer. If you try, those who have tried the answer will understand very fast. Those who didn't have a try, maybe not that easy to understand. Anyway, as I said, the sender always sends in sequence. So we can write definitely 550 equals to 400 plus X, and also Y equals to 550 plus 100, because sender always sends in sequence. So the sequence number of the second segment will be sequence number of the first segment plus data. Sequence number in the third segment will be sequence number in the second segment plus data. So very simple. That means X equals to 150, Y equals to 650. Very simple. Then about Z, Z is the acknowledgement of the first packet that is already sent. Since we know X equals to 150, so it will be 400 plus 150. So Z will be 550. Now Mahir and Sumaya, okay, Moshiur and Moshiur also, whenever a packet is lost, see, this packet is lost, right? So for all subsequent packets, what will be the acknowledgement number? The previous in order, right? We have read about the cumulative acknowledgement. What cumulative acknowledgement says? If you draw the memory buffer of the receiver, you can draw like this. So this is 400. This is received, right? 400 to 550. Then this one, the next one is lost. So there is a gap. Then the third one from 550 to 650, and then 650 to 800, right? So 800. So third one is received. But if I need to get the acknowledgement, this should be the acknowledgement before the gap, right? Agreed?
Yes, sir.
That what we have discussed in the last class. What is cumulative acknowledgement? When there are gaps for any subsequent segment, what will be the acknowledgement? It will be the acknowledgement before the first gap. So there is only one gap. So any packet coming after that gap will have the acknowledgement before the gap. So what will be the value of P? Now, anyone? It will be same as the previous acknowledgement.
550 plus 150.
No, it will be the same, right? Because Z is 550. Z is 550. Next one is lost. So all subsequent packets until the gap is filled up will have 550. So that's why P is 550, right? Agreed? Any confusion? Because there was a gap. Now after the timeout, this one is retransmitted. So the gap will be filled up, right? And now for this acknowledgement, what will be the acknowledgement? Now it will not be 550 plus 100. It will be updated acknowledgement. If the gap is filled up, what is the updated acknowledgement? $800, right?
650 plus 1.
650 plus 150.
Yes, sir.
Right, because just if you draw the diagram, you can be sure if gap is filled up, then for that segment, receiver will send the updated acknowledgement. What is the updated acknowledgement? Up to 800. So Q will be 800, right? Clear everybody now? Any confusion? So the answers from Mahir, Sumaya, and Moshir. You have the problem with P. Whenever a segment is lost, for all subsequent segments, the acknowledgement will be the previous one. Simple. The previous one. This is called duplicate acknowledgement. The same acknowledgement will be sent again and again. If there is another one sent here, then again that acknowledgement will be again 550 because there was a gap. There is a gap in the 550. But when that gap is filled up, then the acknowledgement will be the final, latest one, updated one. Clear? Okay. No question? Okay, if there is no more question, then I think we have covered many examples, 3 interesting scenarios from the textbook. For those who are yet to understand these concepts, maybe you have some confusion still, please go back to the textbook, must. Okay, how many of you use textbook for understanding so far before the midterm? For understanding the basic example from textbook, how many of you? Sumaya, good. Sami, very good. Shafiqul, Mahir, Shaumik. Okay, I think that's fine. That's very good. Many of you, Ammar, many of you have used textbook. My suggestion is go to the textbook at least to understand the example I have covered in the class. That means the example from the textbook I have covered in the workbook or my class. You can go through my lectures again and again. This is an example now because previously when we used to have the physical classes, you didn't have that recording, right? So you have the flexibility now. You can go back and back again, maybe 2 times, 3 times my recording. But it's still, my suggestion is go to the textbook, not just before the exam, not just the day before the exam. During the class, go to the textbook, at least read that part, the basic example I have covered in the class. So that will help you. If you understand that basic example from the textbook, because there are so many descriptions, right? What I am saying verbally, that is written here. So you can point out many things that is not clear from the textbook. But if you just understand from my lecture, that is very good. If you understand, very good. But sometimes it's very tough. If we don't understand the basic example from the textbook, the number of problems we solve, doesn't matter how many solutions I go through, the concept will not be that much clear. Okay? So my suggestion is at least go to the textbook to understand the basic example first, then try the solution or see the solution of a particular exercise based on that concepts. Anyway, let me just stop our hands on here and let me then cover the rest of the theory part of chapter 3 before we go to the hands-on examples again. Okay. Okay, so we have covered how TCP works, and so far the only way for retransmission is timeout. Agreed? When a sender will retransmit, if the timeout expires, right? In go back and in selective repeat, even in TCP, we are always so far use timeout as the only way for retransmission. But sometimes what happens, if you consider the scenario, for some reason one particular packet losses, but network condition is not that bad. So what will happen? Many packets will arrive at the receiver, but for one particular packet lost, we have to wait for the timeout. Now, consider this example. The sequence number 92, 8 bytes of data. First one is correctly received by the receiver. Second segment in the trot is actually lost for some reason, but other segments correctly received by the receiver. And what is the value of timeout? The value of timeout is actually dynamic. There is an equation in the textbook based on RTT. So based on RTT, the timeout is dynamically calculated. Definitely, if RTT is much higher, for some reason, maybe the network is congested, or maybe the distance is higher, or maybe the capacity is less. For many reasons, IoT can vary. So based on the RTT, the round trip time, based on the round trip times of every previous segment or packet, the timeout is dynamically calculated by the sender. But as I said already, TCP uses a single timer. So it is actually that timeout can be longer, timeout can be shorter, it depends. For example, if timeout is relatively large, as you can see in this example, and if some segment is lost, we have to wait for the timeout before retransmit. Now in this case, see, if you think about the acknowledgement, the first acknowledgement 100, no problem. The second one, acknowledgement again 100. Why? Anyone?
Because one data lost.
Right. Whenever a segment is lost, all subsequent segments will have the same
Acknowledgement.
Right? Now, in this case, if you see the first acknowledgement 100 is normal, it's fine. And the second acknowledgement 100 means sender is sure that is a duplicate acknowledgement. So whenever sender receives that acknowledgement, sender can assume, okay, a data from 100 sequence number is lost. But still sender will not right away retransmit, because maybe the acknowledgement will come later. Maybe it is not lost. Maybe the acknowledgement is coming in a different path, so it might have a different delay. But if you receive 3 duplicate acknowledgement, experimentally it is proven, if you receive 3 duplicate acknowledgement, then it is almost ensured that data is really lost. So in that case, without waiting for timeout, you can retransmit the lost data. That is called fast retransmit, FAST, fast, because definitely it will work faster, right? If we had to wait for the timeout, we had to wait for an extra time. But now we can retransmit even before the expiration of timeout, so we can save some time. But it is not 2, it is not 4, it is exactly you have to receive 3 duplicate acknowledgements. Why 3? Because experimentally it was found that if you consider 3 duplicate acknowledgements, then it provides us maximum efficiency, maximum benefit. Clear? So this is called TCP fast retransmit. Okay. Now let us go to one more. Hands-on example, okay? Before I come back here. Okay, let us solve exercise 2. Sumaya, you had a question? Sumaya?
No, sir. Sir, bullet
Okay.
tap kore diyeche.
Okay, no problem. So fast retransmit is a simple thing. It's a you can see here also again, it's a simple thing where before the timeout we can retransmit. So in this example, timeout is shown in a different way. For example, whenever an acknowledgement is received, a new timer is set. That can also happen. But within the timeout, if we receive 3 duplicate, we can retransmit the. Now, one question is how sender will know that is a duplicate acknowledgement. So let us first solve this exercise 2, and then we will come back again to the example. See, it says the sender send base. What is a send base? Actually, if you draw a diagram like this, if you draw it, sorry, I think we should make it more. Okay, so if you draw a diagram, send base equals to 328. Send base actually contains, it contains latest acknowledgement. Okay, so whenever a new acknowledgement arrives, send base is normally a variable, like integer a, integer b. It's a variable. Okay, so it's a variable. It contains the latest or updated acknowledgement. So send base 328 means previously the sender has received the updated acknowledgement 328, right? You understand? So now it says the last TCP sequence number sent was 950. So I can draw the diagram like this. The last sequence number is 950 and the data is 500 bytes. Okay, so it will have receiver will send an acknowledgement sometime, but it says a segment is received with TCP acknowledgement number C 350 and window 3000. Now acknowledgement number is 350. What is the acknowledgement number of this segment? What is the acknowledgement number of this one? 950 500 byte. What is the acknowledgement number?
1450.
Right, very good. 1450. So that means this acknowledgement is not received yet. You received an acknowledgement of a previous segment. Is the logic clear? Because it says 350. So you can draw like this. From a previous acknowledgement, you have received an acknowledgement number that is 350, and then in that case window is 3000. Now we have to understand clearly. See, even if the question didn't ask you to draw a diagram, if you draw a diagram in, especially in TCP, that will be easier to understand. First let us find the solution for question number 1. That is very simple. What is the new value of send base? Anybody? What will be the new value of send base?
350.
Very good, 350. It's a new acknowledgement, so it's 350. So previous one will be replaced. Definitely it will be 350. Now what is meant by an acknowledgement number 350 with a Windows 3000? See, we have given you the concept of flow control. That receiver calculates its free space and then sends the feedback to the sender, so that sender knows how many bytes I can send without overflowing the receiver's buffer. So again, if you draw the buffer of the receiver, can I write like this? Up to 350, all the segments are acknowledged. All the bytes up to 350 received by the receiver. Is it correct?
Yes, sir.
Acknowledgement number 350 means that. And by that time, it says window 3000. That means I have further 3000 bytes free space, right? 3000 bytes more space I have, receiver says to the sender. When it sends an acknowledgement of 350. So can I say this particular byte number is 3350? Yes or no?
Sir.
So 350 plus 3000, simple, 3350. Now come back to the second question. It says, what is the last byte number that can be sent with certainty that the receiver's buffer will not overflow? Actually, this is flow control. But the question asks, what is the last byte number? What up to which byte number sender can send to by ensuring that receiver has still a space, receiver will not overflow. Can I
3350.
say that? Yes, 3350. So you can calculate this like this: last acknowledgement plus the window, already given in the question. But if you have the concept, that is very simple. So 350 plus 3000, so it is 3350. Everybody okay?
স্যার
জি
এখানে
স্যার।
যদি আরো একটু
Because
কোশ্চেন হতো
yes,
যে another TC acknowledgement নাম্বার 3 সাপোজ 340 তে আসছে, তাহলে কি এটা আবার 340 আমি যোগ করতাম?
okay, I'm not sure. Okay, Mahir, let me maybe I got your question. Let me explain in a different way. TCP, both sender and receiver, we already mentioned the communication is bidirectional. So sender can also send data, receiver can also send data. So sender has a actually buffer as a byte stream, and receiver also has a buffer as a byte stream. If you generally think, okay, this is sender's buffer, this is receiver's buffer, but for simplicity, we always ask questions one way, as if this is sender, this is receiver. Actually, receiver can be also a sender. So how this actually works, for example, it starts from 1101 to 1200. So 100 bytes of data should be sent to the receiver. So it's a scale of bytes. Similarly, receiver will receive this and receiver will store in its own buffer, and then receiver will calculate the free space. Now what happens, see, the last TCP sequence number sent, that means before this segment, sender has already sent some other segments for which it did not receive any acknowledgement. Correct or wrong? Because I received a acknowledgement 350 and the last sequence number has sequence number 950. What is the data bytes between 350 and 950? Where are the data bytes? Right?
Yes, sir.
Can we say according to the, although the question actually did not ask that, but to understand better, can we say from 350 up to 1450 data has been sent but no acknowledgement yet received? Can I say that?
Yes, sir.
Right? If you think, because sender has received acknowledgement only 350, but sender has already transmitted up to 1450, right? So that means this green part, the data maybe is not yet received by the receiver, or maybe receiver has received but the acknowledgement is not arrived at the sender. So this is another thing. But until sender receives an acknowledgement, sender cannot assume that receiver has received all. Sender will only be sure when sender receives an acknowledgement. So in this case, I can say, I think we have seen one diagram in last class where we said received and acknowledged, sent and acknowledged, sent and not acknowledged, right? Sent yet not acknowledged, and then another part is still not sent. So that is still not sent, can I say that part is here? This is still not sent.
Yes, sir.
Yes, sir.
Right? So if you understand the diagram, the answer to the question will be very simple. That's why I say don't understand the solution, understand the concept. Now if I change this question like how many bytes still sender can be sent after the last segment, can you calculate that? The question says sender received acknowledgement up to 350, but sender has sent data up to 1450. That means sender can send still some data. How can I get that data?
বিয়োগ
If
করতে হবে
I
স্যার।
Sir,
right,
check করতে হবে।
So
if I
1150.
say
So 1100.
no, I don't know, if I minus 3350 1450 to 3350, can I get that?
1900
Right. Because question B, actually that is not the question asked here, but I can ask the question. I can change the question like this. So the second question B says, what is the maximum byte number, last byte number that can be sent? That is 3350, we know. But if I ask how many bytes after the last segment, so up to which byte in last segment sent? 1450. So how many bytes still can be sent? Not yet sent, still can be sent. If I minus 1450 from 3350, I get that. So it is what? 1900, right? So I can say this is the number of bytes, just for understanding. Question is not asked here. Number of bytes still can be sent. It can be a question. What are the number of bytes still can be sent by the sender after the last segment? So after sending 1450, how many bytes still can be sent by the sender? Clear?
Yes, sir.
And you can say until another acknowledgement is received, it is being said. Because if you receive another acknowledgement, window will change. If you receive another acknowledgement, then the window will change, because that will change the free space in the receiver's buffer. So in any case, the data given in the question you can draw. If you have the concept clear, any question you can answer. Very simple. Okay, question C. What is the next byte number that will be sent? Easy. What is the next byte number? That will be sent by whom? By the sender or by the receiver? What do you think? By the sender
By the
or by
sender,
the...
sir.
Definitely by the sender. So what
Single
will be the
bit
next
decimal.
byte number? How can I get that? 950 plus 500. So that is the next segment. What will be the sequence number of the next segment? So it is simple. Clear, everybody?
স্যার আরেকবার বুঝিয়ে দিলে ভালো হতো।
Which one? Question C or question B?
স্যার কোশ্চেন সি।
Question C. Question C says, okay, question C says, if you think about question C, that means you will send a new segment, right? Question C says, what is the sequence number of this segment? The same question. If I ask what is the sequence number of the next segment that will be sent by the sender, or if I ask what is the next byte number that will be sent by the sender, this is same. So if I say what is the sequence number of the next segment, what is the sequence number? You will add 950 plus 500, right? Because sender
Yes,
always
sir.
sends sequentially. So that is the answer. Next byte number is the next sequence number, because sequence number is the next byte number of the next segment, right? First byte number of the next segment. So if you understand the concept, the language will not be a problem. But if you don't understand the concept, you understand the solution, then language will be a problem. If I change the question, okay, Monsieur.
Sir, when we send 1450 bytes at first, then
Yes.
I got the acknowledgement of 350 and the window of 3000. Like, I think 1450 bytes has already consumed, right, sir?
Right. Yes, your idea is correct. If I think about up to 1450 already sent, and then the next segment will start like this, right?
Yes, sir.
From 1450. So that is the point. It will start from 1450. I don't know how many bytes can be sent, because I cannot know how many bytes. And the question cannot ask you how many bytes will be sent in this segment. But the question asks you just from which byte number the next segment will start. Got my point? Mushir?
Yes, sir.
Yes. So the question, because how many bytes will be sent here is no information given in the question. So we are saying that there will be a new segment that will start from 1450, but how many bytes we don't know. But definitely there will be some bytes, finite number of bytes in that segment, but that is not part of the question. But that can be part of the question if I give you the more information, and based on the information, if I ask you some question, I can ask. But I think the exercises we have solved, exercise 3 and 2, and the interesting scenarios from the textbook covered all possible angles of a question I can ask. There is no more different angles or patterns, but maybe I can change the data. If you draw the scenario, it will be simpler. Okay,
Sir,
everybody clear?
one more question, sir.
Yes.
Sir, how much
Yes,
time
sure.
we need for what is this?
How much
Yes, sir. How
time or
much time actually, sir? When we declined a request, so how much time we need for that time, sir?
decline a request means what? In this example, exercise 2, or you are asking in a separate question?
I'm asking for a separate question actually, sir.
Monsieur, okay. How much time? That means, is it timeout? You're talking about timeout, or
Yes, sir. Yes, sir. Time out, sir.
Timeout is dynamic. Timeout for every uh, timeout set, it can vary. Like for example, the previous timeout is 1 millisecond, but new timeout is maybe 2 millisecond or 1.5. It depends on, as I said, there is an equation actually used by the sender every time it receives a feedback. So it recalculates the RTT. Based on RTT, there is an equation. We are not going to cover that. There is a complex equation that actually sets the timeout. But what we have to keep in mind when we think about the timeout, it can be too short, it can be too long, because it is dynamic. How I am saying that it is too short or too long? Because there is a theoretical timeout limit within which acknowledgement should come. But acknowledgement is sent by the receiver, timeout is set by the sender, right? So sender has no control on acknowledgement, receiver has no control on timeout. That means it can happen, acknowledgement can come after the timeout. We have seen already that situation. Or timeout can be longer, and we have seen the fast retransmission mechanism so that we can save some time. Okay, Mushir. So
Sir,
timeout
is it actually depends on size or the distance? Actually,
it depends on RTT. Like if if the previous RTT shows that the sender is receiving acknowledgements with longer time, that means RTT will be longer, right? And if RTTs are longer, then the next timeouts will be longer. It's logic. But network condition can vary significantly within a short amount of time. So that's why we have to have these mechanisms of retransmission. Even if retransmission is redundant, we have to do that. But yes, timeout can be too short or too long, because sender will not see what is actually happening in the middle, right? Okay, now let us then go back to our rest of the theory part. Okay, so we have covered fast retransmission here, and now I can ask you one question: how sender will know this is a duplicate acknowledgement? Because sender stores the acknowledgement in a variable called what? Send base, right? So if send base contains 100 for the first acknowledgement, and if it receives 100 again, then sender is sure this is a duplicate acknowledgement. This is very simple. That acknowledgement already in the send base is again received, that means it's a duplicate acknowledgement. So sender can use a counter. If count 1, 2, 3, At that time, sender will retransmit. So that is the idea how fast retransmission is implemented. But fast retransmission is not supported by all the TCP protocols. It depends on the different versions. Okay, can we move? If you have any question, you can ask. The next topic is flow control. And we already mentioned flow control several times, that the receiver, after receiving a segment, every time it receives a segment, it recalculates its free space in the buffer, and then it sends the acknowledgement to the sender. So sender knows how many bytes I can send. Already we have seen exercise 2, an example. And in now one concept how this works, because we know flow control is implemented in TCP, that is transport layer. It depends on IP of network layer, and also we know there are sockets for every connection, and every socket has a corresponding buffer where application stores its data. Transport layer at the sender receives and then creates segments. Transport layer at the destination, that means receiver, will store the segments. When all the segments without any gap of a message fully received, then application will receive the data from the buffer. When application receives the message, then the buffer again freed up, right? So the window will change, and then in the feedback, receiver will inform the sender that I have that much amount of free space. Otherwise, once it is occupied, it would have been never free, right? But it will be free when application receives data from that buffer in the socket. So this is the top level view. Now, how every time receiver calculates, so this is actually overflow. When you can see in the diagrams, much water is actually spilled or overflowed, what they can receive. So this is like the flow control, and this is controlled by a value. Already we know the field receive window. Every time receiver calculates free space and then stores that value in the receive window field, and after receiving the feedback, sender knows how many bytes I can send without overflowing. This is called flow control. And how this is calculated, you can see on the right side. Very simple. This is a buffer. This is a memory. So if you think about the memory, there is a occupied part. That is buffer data, means all the segments are occupied here, the blue shaded area. And the gray shaded area, light area, that is a free buffer space. Now the total buffer is receive buffer. If total buffer size is receive buffer, and if I deduct from the receive buffer the total amount of data received, definitely I can get the free space. And this free space is called R window. R window for receive window. Okay, so this R window is calculated by the receiver and then sent with the acknowledgement to the sender. Clear? Calculation is very simple. Okay, like this. Next part is, this is again a very small part. This is the connection management. For connection management, as we said, TCP must establish a connection, then TCP can transfer data. So the previous examples we have seen, when TCP transfers data, we have assumed connection is already established. And then after data transfer is complete, then connection must be again closed in a predefined manner. So how connection is established? It is called TCP three-way handshake, because there are 3 steps. And as I mentioned during in the last class, I think there are some control bits in the TCP header. These control bits are used for connection establishment. For example, when a client wants to create a new connection with the server, it cannot send the data right away. It must send a connection request segment. How receiver will understand or server will understand this is a new connection request? Because in that case, that control bit, SYN bit, will be 1. SYN bit will be 1 where there is a new connection request. And also the sender will specify its own initial sequence number of the scale of the set of bytes it will send. After receiving the initial request, the server will again create its own parameters. I think it will store the buffer, create the buffer, create the socket, and then it will send an acknowledgement to the client that I have received your request. This is again, SYN bit is 1 here, and acknowledgement bit is also 1 here, and sender or server sends its own sequence number, that is Y. So the client sequence number was X, sender sequence number, server sequence number is Y, and server will send the acknowledgement number X plus 1. That is the idea, because there is no data here. So it will just add 1 to the previous sequence number in a step 3, but still data cannot be transmitted. In a step 3, now data can be transmitted or connection is established, because client now sends a third segment with acknowledgement bit 1, but SYN bit is now 0, and SYN bit will remain 0 for entire data transmission time. Okay, and the acknowledgement is Y plus 1. So now connection is established. See, both sides, client is established, server is established. Data communication starts. And how data can be synchronized, we have seen already many examples. Suppose data connection, I have completed downloading a file, data connection is complete. Now, next part is closing a connection. Again, you cannot close right away. Or as a user, you can click the cross, you can click the browser, you can close the browser, but the underlying coding must follow this procedure. What is the procedure? Again, client will send a new connection closing request to the server. As a user, I cannot see that, but this is being done inside by the browser, where fin bit equals to 1. Then server sends an acknowledgement bit is 1, but server says, see, I have received your closing request, but I cannot close right now because I have opened many database, many files, many things. I have to close my processes. Then I will let you know. So server does actually its own works. After completing this, then server again sends a new closing request to the client. See, I have finished my work. Now you can close the connection, but you have to send me the acknowledgement. And finally, client sends an acknowledgement. If server receives the acknowledgement, server can be closed right away. And after sending the acknowledgement, client waits for a predefined amount of time to make sure server has received that segment, and then client also closes. So client closes later, server closes earlier. So these are the steps for closing a TCP connection. So if you see the cycle, life cycle of a TCP connection, you can see it must be established. A connection must be established. Then data can be transmitted for a longer amount of time. Then after data transmit is complete, the connection must be closed in a predefined fashion like this. So this is called connection management. Any question? Okay. Last topic of chapter 3 is congestion control. Now, what is congestion? That is the traffic jam. We are very familiar with traffic jam, right? Why traffic jam happens? Anybody? What is the main reason? I know we have many reasons in our country, but generally, what is the main reason for traffic jam? More number of vehicles than the capacity, right? And also the office time, too much traffic jam, up to a certain amount of time. Same thing happens in network that we call a peak hour, off-peak hour, right? But how congestion happens? Congestion is like traffic jam. It happens when the capacity of a link is overwhelmed by the amount of data. If the capacity is less than the demand, what will happen? The line will grow, the queue will grow. And if the queue is filled up, packets will start to be lost. So packet loss in networking can have two reasons. One, we have mentioned, both we have mentioned in the chapter 1. Can anybody tell me what are the possible reasons for packet loss? One is error, right? Another one? Right, buffer is full. So no space in the buffer. That is also packet loss. There is no error, but there is no space to store the packet. So what happens when we send too much data over the capacity? First, all the devices, intermediate device, end device, they are especially the intermediate devices like routers, because all packets go through the routers. Every router has a limited buffer. So first, router start to fill in the queue, store in the queue, buffer. Then buffer is filled up. Then definitely packets will be lost. If packet is lost in a particular router, doesn't matter in which router packet is lost, the packet is lost forever. Forever. It cannot be reconstructed. It must be retransmitted. As we said, the transporter will take care. So the one informal definition of congestion can be all too. Too means too much. Too many sources sending too much data too fast for network to handle. That means it's over the capacity for a longer amount of time. And after a certain time, there is no more space in the buffer also to store. So there are two problems in congestion. Number one, long delay. Definitely there will be long delay. Number two, packet loss if buffer is full. So if you unrealistically assume buffer is infinite, then the delay will be close to what? Infinite. So that is the problem with congestion. So what we have to do, we have to control the congestion. Idea is very simple. Idea is in networking very simple. Every node, when it sees that, okay, the packet I have sent is lost, it will assume there is a congestion. Then what it will do? It will reduce the rate. It will reduce the rate. If previously it sends 10 kbps, now it will send the data in 5 kbps like this. And if every node reduces the rate, what will happen? Congestion will control, right? After a certain amount of time, congestion will be controlled because every node is sending, now reducing the sending rate. That is the idea. But if we reduce the rate, what will be the problem? If we always reduce the rate, then there will be again another problem. What will be the problem?
Buffer full.
No. Delay. Problem will be delay. If we reduce the sending rate, our ultimate transmission rate will reduce. So what can happen? Sometimes it might happen network has larger bandwidth. I am not using the bandwidth. So it's a continuous process. If there is a loss, reduce the rate. If there is no loss, what? Increase the rate. It will be continuous. It is called probing the network continuously. So this is congestion control, but this is different than flow control because flow control only depends on free space in the receiver's buffer, right? But congestion control depends on all the intermediate links, all the nodes they are participating. If participating nodes are larger, if the data they are sending larger, then there is a congestion. And we cannot handle the links in the middle. We can handle the transmission rate by the same. And it is a very important problem in networking. One of the top 10 problems still, because with the advancement of the technology, we can have more and more bandwidth available, but at the same time, we can have applications or services requiring more and more bandwidth. It's a never-ending process. So still it's a top 10 problem, congestion control. Now there are two approaches we can deal with congestion control. One is end-to-end, where the end systems will only participate. The host or devices that sees a congestion will reduce the rate. That is end system. TCP uses this, and we will actually concentrate on this version, congestion control by TCP. But there is another one, that is network assisted congestion control, where the routers, the intermediate nodes can also participate. The logic is a router, if a router has seen that the connection with the router, one link with the router is occupied, overflown, then it can send back to its previous router, right? That, okay, don't send me packets to this way because this is over congested. So the previous router will reroute the packets to other paths if exists. Otherwise, it will wait. So that is another way, network assisted congestion control, but we will cover only end-to-end congestion control in this chapter due to lack of time. Okay. So there are some protocols, TCP, CN, ATM, but we will cover only end-to-end TCP congestion control. So there are three approaches we will discuss, but generally, as I said, the approach is simple. If there is a loss, the node will reduce the rate. If there is no loss, the node will increase. It will be continuously happening like this. The first one is AIMD. AI means additive increase. MD means multiplicative decrease. So like this, normally the time is measured in terms of RTT, round trip time. So if in first RTT data is sent one segment, that is one MSS. MSS is maximum segment size. So if one MSS is sent in an RTT and there is no loss, then in the next RTT, how many MSS will be sent? 2 plus 1, additive. In the third RTT, 3. In the fourth RTT, 4, right? Unless there is a loss. So that is called additive increase. Increase one segment at a time in each RTT if no loss. But if there is a loss, then if you just reduce the rate a little bit, it will not help. Because there are many nodes, suddenly there is a congestion. If you remove one car at a time from the road, it will take huge time to remove the traffic jam, right? But if you can reroute the vehicles, cars to different roads, or if you control the signals, then it will be easier to control the congestion. So what happens when there is a loss? The decrease is multiplicative. That means it will not be one segment, it will be half. Directly it will be half. So if it's half, it is called multiplicative decrease, and it will help us to control the congestion more efficiently. Okay, so AIMD works like this. It is called the sawtooth behavior. You know the sawtooth, korat diye gach kate, right? Sawtooth. So yes, sawtooth like this. So when there is no loss, increase, but increase sequentially, one by one. So it will be increased in a slope. Whenever there is a loss, drastically means make the rate half. You can see every loss, every downfall represents a loss of a packet. So the rate will be the previous rate divided by 2. So that is the idea. So if the previous rate is higher, then half will be just every time it will make half. So it will work like this. This is called additive increase. Increase one at a time, and then multiplicative decrease. Whenever there is a loss, cut at half. Now there is one problem in AIMD. If you increase one by one, see there is a theoretical peak, right? Although it is practically not possible to know what is the theoretical peak rate at which I can send so that there will be no loss. It's not possible. So what we can do, we can just increase. Many nodes are working in this way. So at a certain point, packets starts to be lost, right? But if we reach the peak in a longer amount of time, this is disadvantage. Why? Because that will make the available throughput less, right? If we can go to the peak in a shorter time, definitely we can get better output. Do you agree? Yes or no?
Yes, sir.
For example, from this point, the peak is here is reached. The time needed, you can see the lower x-axis. The time needed is, for example, x. But if we could have reached the peak earlier, then the time needed will be much less, and that will actually increase our transmission rate. So that's why the second one is slow start. Let me skip this one right now. Slow start. Slow start says, okay, we'll start from one MSS. Now see the previous case in the flow control, we said R window, receive window. In this case, there is another window here. This is called congestion window. congestion window is how many messages, how many segments, how many MSS we can send within an RTT. That represents a congestion window. So initially we'll start with 1 MSS, but if there is no loss in the next RTT, we'll make it 2. No loss in the next RTT, we'll make it 4, then 8, then 16, then 32, then instead of +1, +1, +1. So definitely we can reach the peak very fast, right? So it will take very less time to reach the theoretical peak. Agreed? So it will be much more efficient in terms of transmission rate. But there is again a problem here. Anybody has any idea what will be the problem here? Just assume that there are many nodes, huge number of nodes. Each node is applying this. So if each node increases exponentially, what can be a problem? Possible problem? Suddenly, there will be huge demand, right? From 1 to 2, 2 to 4, 4 to 8, no problem. But when it goes to 8 to 16, 16 to 32, 32 to 64, see every jump, 64 to 128, jump higher and higher. So there will be a time when the theoretical peak will be exceeded suddenly and huge number of packets will be lost, right? You got the logic?
Yes, sir.
Okay. So because we are increasing exponentially, suddenly with a larger jump, it might happen many packets lost simultaneously. So we don't want that. So that is the second approach. And the third approach actually mixes this up. We will mix the first two. We will increase exponentially until a certain point. After that, larger jump can create larger huge packet loss. So then after that point, we'll increase sequentially. So this is merging the previous two. And what will be the value of that threshold? It depends. It is called SS threshold. It is the slow start threshold. The idea is the threshold will be set. So up to the threshold, increase will be exponentially. You can see here 1. Then in next RTT, this transmission round 1, 2, 3, 4, these are RTTs. And congestion window is our segments in terms of segments. But you can convert this to a rate like kilobits per second, megabits per second. But you can think about this as number of segments or number of MSS. So for time 1, it will be 1. For time 2, 2. Time 3, 4. So 1, 2, 4, 8. Then the threshold is reached. And then 8 to 9, 10, 11. So that whenever a loss happen, it will not lose a huge number of packets. You got the idea? But now how this SS threshold can be calculated, that is another issue. One more issue is how the loss is detected. In AIMD, if a loss is detected, always it becomes half. Rate is reduced to half. But in slow start and the third approach, slow start with congestion avoidance, we have to think about how we have detected the loss. We can detect the loss in 2 ways, right? One is timeout. Another one is what?
Packet loss.
Not really. Just we have studied in today's class. Fast retransmit. When we can retransmit before the timeout? When? After receiving 3 duplicate, right?
Yes, sir.
After receiving 3 duplicate. So there are 2 ways. Now, can you tell me intuitively in which case I can say network condition is better? If I detect the loss for timeout or if I detect the loss for 3 duplicate?
So 3 duplicate.
Definitely 3 duplicate, because 3 duplicate indicates that I don't need to wait for the timeout. That means many packets are correctly received by the receiver so that I can receive 3 duplicate acknowledgement before the timeout. So that means it represents the better network condition. So in case of slow start and congestion avoidance, if the loss is detected for timeout, then it will again start from 1 MSS. It will again go to the first step, 1 MSS. and then increase. But if the loss is detected to 3 duplicate, then the rate will be half. The rate will not be 1. The rate will be half of the current congestion window. So that is one thing. And SS threshold, whenever there is a loss, the SS threshold should also change. But doesn't matter, the loss is due to timeout or 3 duplicate, the SS threshold will be half. Okay, always half. The congestion window will be half if detected by 3 duplicate. Congestion window will be 1 if detected by timeout. But SS threshold will be updated whenever there is a loss, but it will be always half of the current rate. We'll do one hands-on example next at the start of next class. I think then it will be much more clear. And also another important thing is TCP has many variations, many protocol variations. There are 2 examples in this diagram. One is TCP Reno, one is TCP Tahoe, to indicate not all TCP variations support fast retransmit. As you can see here, suppose the loss is due to 3 duplicate. So for fast retransmit, it will be half, right? The rate will be half. But in case of TCP Tahoe, see, the rate is 1. So TCP Tahoe does not support fast retransmit, does not support 3 duplicate. So for any loss, it will come back to 1. Because TCP Tahoe does not support fast retransmission. TCP Reno, this is a variation of TCP. It supports fast retransmission. So see, in this case, it actually makes, for a loss, reduce the rate to half, and SS threshold also reduced to half. So in case of TCP Tahoe, it again increased up to the threshold, then sequential. In case of TCP Reno, it started from the SS threshold and then increased sequential. Clear? Any question?
Sir, we have 3 approaches for this congestion control.
Right.
Actually, practically, sir, which one we use actually?
Actually, none of these used practically because these are all very primitive approaches. As I said, it is a top 10 problem. So there are so many efficient algorithms proposed, used in the industry. But to understand those approaches, we need to understand these 3 approaches. So maybe not anyone is directly using, but the approach, any congestion control using definitely one of these approaches, but they use these approaches with much more efficiency. Like TCP Tahoe is very inefficient protocol. TCP Reno, much more improved. There are so many newer variations. It is continuously being evolved. TCP New Reno, TCP Vegas. There are so many versions. In your textbook, you can go through, you can have some of the TCP variations, but it is continuously being changed. It is changed for a different type of networks. For wireless networks, it is changed for mobile networks, cellular networks, it is changed for IoT. Continuously it's being changed. But the idea is, if we understand the approaches of congestion control for 3 basic approaches, it will help us to understand any practical approach currently being used, right? So
Yes, sir.
I think you have some confusion still, but during the start of the next class, we will do a hands-on from this congestion control, from a scenario. We'll calculate the values. I think then it will be much more clear. Just if you go through the textbook, as I said, if you just try to understand what is the concept, then this will help us in the next class when we do some hands-on. Okay. Okay, so that is actually the end of our chapter 3. If you have any question, we can discuss. We have 2 or 3 minutes more. Okay, and those who have joined later, we have our class test 4 on 11th September. I will confirm the syllabus and online or offline in the next class. Okay, and I am in the process of your midterm script checking. When all the scripts will be checked, I will upload all the checked scripts as early as possible to the ELMS. No more question? Okay, then let us finish for today's class. See you in the next class.
Sir,
Yes,
Sir, attendance.
I have already taken the attendance.
জি স্যার, আমার ইলেকট্রিসিটি ছিল না তো আমি
Okay,
late
okay.
করে-
Send me an email.
ওকে স্যার।
Okay.